So we were deriving an F distribution. What's an F distribution? A Fisher F distribution. So F is equal to U. What's an F distribution in words? Other than Ernest. Ernesto. Esteban.
The ratio of two chi distributions divided by their degrees of freedom.
Exactly. The ratio of two chi distributions, two independent chi's. So U is a chi squared with n degrees of freedom. V is a chi squared with m degrees of freedom, and they're independent. We took this ratio, we did the computation. Did you do it at home? Did you finish the computation at home that we didn't get to last time, or should we continue where we left off? Do it again? All right, let's finish it. Let's finish it. Okay? So again, let's do it. So we want to know what the probability is that f is at most a. That's the integral. So we're going to have two things, and we saw that it was more convenient to take the v variable. So v will go from 0 to infinity. There's an f chi squared of v with m degrees of freedom, dv. There's a u integral. The u integral goes from 0, well, in principle to infinity, but we're bounded by the condition f is u over n divided by v over m, and this is at most a. So u will go up to v times n over m. That's the upper range of u. F chi squared n of u du. Does everyone agree with this formula? So this is the integral over all possible values of u and v with their PDFs. U is distributed as chi squared with n degrees of freedom, v is a chi squared with m degrees of freedom, but the range of u is restricted so that this inequality holds. U divided by n over v divided by m, which is f, is bounded by a. Is this big enough in the back? Need me to zoom in, or it's okay? I mean, I guess in principle I can zoom in. Okay. So, what did we do? Is this correct? There's no a. There's no a. What happened to a? A is here. So we solved for u by moving this to the other side. You get a times this stuff. So there's a missing right there. A, v, n over m. What we want here is not an a times that stuff, but an a by itself. So we make a change of variables. What do you want to call this? T or something? Let t equal u divided by this stuff, divided by v over m over n. In other words, t is the original f variable, so that indeed goes up to a. dt over t, how does that compare to du over u? They're equal. That's the beauty of this par measure. So we'll put in what this is in a second. So when we make this change of variables, this probability becomes still an integral in v from minus infinity, from 0 to positive infinity. Instead of u, we have t. This change of variables, this is a positive constant. So t still goes from 0. But now when u is equal to a times v times n over m, when that's replacing u, t goes up to a times that crap divided by that crap. That was the whole point of the change of variables. So we get an a up top. Okay? There's an f. What is f of chi squared over n? It's 1 over 2 to the n over 2 gamma of n over 2. Those are just the constants. There's an e to the minus u over 2. But it's not u anymore. It's t times v times n over m. Let's just solve for u here. U is equal to t times v times n over m. And so that's what, it used to be e to the minus u over 2, so this is tv n over m. And then there's a factor of u raised to the power n over 2. And then du over u, which we already know is dt over t. U raised to that power is t raised to that power. We can go ahead and break these up, times v raised to this power. V n over m to the n over 2. That finishes the u integral. Then I have the v integral outside of everything with m degrees of freedom dv. Any questions? Folks are still writing. Give them a second to catch up. This was e to the minus u over 2, and u raised to the n over 2 power, du over u. Okay? Now, who knows what you're going to do next? Can I see a show of hands? Handful of people. So let me give you a minute to think about what you would do next, if you don't already know. How do you simplify this? Well, one thing we have to do is we have to put in what this is, right? We want to just get an integral from 0 to a of something, and that something will be the PDF of your F distribution. So Taylor, your hand was up.
Are we just gonna do like the substitution?
Yep. So we're going to do a substitution to evaluate the v integral explicitly.
Oh, so we have to switch.
So we have to switch orders. Yeah, we want this integral outside. So we switch orders. Fabini Tonelli. T will go from 0 to a. Let's pull out all the constants we can. 2 to the n over 2, gamma of n over 2. And let's pull out anything that only has to do with t's. I see a t to the n over 2 dt over t. So I've taken care of this. I've taken care of this. Let's pull this n over m to the n over 2 outside also. N over m to the n over 2. So I've taken care of this. And this constant and this integral. So now we need the rest. The rest is an integral in v. V goes from 0 to infinity. I've taken care of that. I have this thing which has a v in it, so that's an e to the minus t v n over m over 2. There's a factor of v to the n over 2 from here. And finally, the chi-squared with m degrees of freedom, for which we know the PDF. What's the PDF? Sakina?
Is it 1?
The PDF of the chi-squared with n degrees of freedom? We wrote it down already for you. So it's 1 over these constants. Do we need to recall this? The chi-squared? No, we know the chi-squared for m degrees. Okay. It's 1 over these constants, 2 to the m over 2, gamma of m over 2. Those are just normalizing constants. Then an e to the... I said it already, but I want to... So you've answered the question, Zach. The other... Is it just too hot in here to focus? And it's like Friday and spring break? All right, let's move. We'll write these things down, and then we'll deal with them later, dv over v. Okay? So there's a constant, 2 to the m over 2, gamma of m over 2, e to the minus v over 2. The power is v to the m over 2. M is the degrees of freedom, dv over v. We're going to do the thing that we've done 1,000 times, which is Jasandeep? Yep, we want to make it look like a gamma integral, exactly. So we'll take, we'll combine the exponential terms. So the exponential terms are e to the minus v times something. Here I have a half. Well, there's a half in both places, so let's pull the half out. And so now I've pulled out everything, so I just get a 1. And what do I get? What am I left with here? Dylan?
1 plus TV n over m.
Yes, and the v I've pulled out,
So n over
so just n over m is left. Okay, that's the exponential term. And then there's a polynomial term. Let's grab that too. The polynomial term is v to the power n over 2 and m over 2, so that's n plus m over 2. Is everybody happy with that? Okay, page 2. So what's my change of variables going to be? To get a gamma function, as Jess and Deep said, I want this to be e to the minus something, right? Not something with crap. So my change of variables, I need this thing to be one variable. What variable should I, do you have a name you want? W or something? Z? Z? Okay. So now make another change of variables. Let z equal v times crap, 1 plus t n over m over 2. These are all constants. This is an inside integral. The value of t has been fixed. T is a constant as far as z is concerned. It's a change of variables in v. There's my favorite factor, dv over v. What happens to dv over v? dz over z. So the whole thing becomes an integral as t goes from 0 to a. I got a bunch of constants here. Let's keep track. N over m to the n over 2. There's a 2 to the n over 2. Gamma of n over 2. There's also these 2's and gammas. Let's get those. 2 to the m over 2 gamma of m over 2. So we got those constants. Is that all my constants so far? And then an integral in what used to be v is now z. This is a positive number. T is positive, n and m are positive. So z now ranges from 0 up to infinity. What is the exponent? Z. The whole point of this change of variables is that this whole thing gets called one letter. So e to the minus z, exactly as we wanted. Now we had v to a nice power. Now I have, instead of v, I want to write z divided by this stuff. So let's solve for v. Off to the side somewhere. V is equal to z divided by this stuff, which is z divided by 1 plus t times n over m. Divided by 2, which I'll put in the numerator, times 2. Just solving for v as a function of z. So I move the 2 to the numerator, and then I put this in the denominator. So far, so good? Okay. So that's what v is, and I want that to the power n plus m over 2. So here I have a z times 2 divided by 1 plus t n over m. It's very messy, but it's going to simplify. I mean, I'd like to say a lot. It will simplify a lot, but it's still, I mean, it's not a pretty distribution. It's not something you would just dream up. Like a Gaussian comes out looking kind of pretty. This doesn't, but that doesn't mean it's any less valid as a distribution. We shouldn't call it names or something. Okay. dv over v is a dz over z. That's my inside integral. Then I still have, don't forget this power of t, t to the n over 2, dt over t. Let me give you a second to catch up to here. Any questions on how I got that? Could you do this on the midterm? If I said derive the F distribution?
How much time?
On the midterm, you have an hour and a half.
For this one problem.
And what if it was?
I mean, it's like a T distribution, right?
It's just like the T distribution. It's
just more stuff.
it's a little uglier than the T distribution. I mean,
more junk.
it's basically just as ugly as the T distribution. There's nothing to it, but several very, once you've had some experience with it, once you've done this like 10 times at home, you're going to be able to do it in your sleep. You wake up at 3 a.m., oh my God, what was that F distribution again? Well, there it is. Okay, now I can go back to bed. What? Maybe. Got to do it a few more times, yeah. Okay, so far so good? What are we going to do? It's a gamma, exactly as Jasandeep said. Integral from 0 to infinity, e to the minus z, z to some power, dz over z. Beautiful, that's a gamma. What's the gamma? N plus m over 2. And then we have this stuff to deal with. There's only one thing left to observe, which is that there's a power of 2, 2 to the n plus nm over 2 in the numerator, and in the denominator. That's the only other thing that simplifies. So this power of 2 and that power of 2 is killed by that power of 2. There's an integral from 0 to a. This constant, n over m to the n over 2. These constants, gamma of n over 2, gamma of m over 2. There's a power of t, so let's keep track of the powers of t. There's a t to the n over 2 and a dt over t at the end. And then there's a 1 plus t times n over m raised to the negative n plus m over 2 power, because it's in the denominator. And now I've taken care of everything. The 2's are gone. The gammas are still there. This exponent, this polynomial term is still there. And all that's left is the z integral, which you already told me how to evaluate. It's another constant. The constant is the exponent. That's it. There's nothing more to do. This is the PDF of a T distribution. Of an F distribution. F sub F of T is equal to the stuff in the box. Any questions? If you can do a T distribution, you can do this distribution. It's ever so slightly nastier looking when you first see it, and then you learn to love it, like any child. They come out a little ugly at first, and then they become yours. So you have to make this yours. You have to do it enough times until it's not somebody else's. It's not Fisher's anymore. It's your F distribution. Taylor.
So I feel like this is a dumb question, but
There's no such thing. Go on.
no, but like I know. Okay, I understand. Like we do all the whole chi-square thing, and then we do all that stuff. But whatever happens to the n and the m that the u and the v are over? Like, why aren't we dividing them by? Like, why aren't we writing the chi-square divide over n when we're putting them into the distribution?
Ah, excellent. Excellent. So Taylor's question is, it's not at all a dumb question. It's a fantastic question. The question is, we're defining an F distribution. Let's go all the way back to the top. We're defining an F. It's a key question. We're defining F as chi-squared divided by its degrees of freedom and V divided by its degrees of freedom. But remember what distribution is chi-squared. So let's go back to how we're going to use this. How are we actually going to use this? We have two sample variances. We have a sample variance from observations A and another one from observations B. And remember, so we have chi, I guess, A, 1 through chi NA, A. These are IID Gaussian. And the same thing with B's, chi 1B up through chi some other number of observations B. They're also IID Gaussian with different means and variances. What is the chi-squared variable?
Isn't it like the sample variance over the like n-1?
It's n-1 times SA squared over sigma A squared. So if you remember the way these are defined, let's recall why this is the case. The way this is defined, SA squared is the sum of the chi I A's minus their chi bar squared divided by NA minus 1, right? This is I goes from 1 to however many measurements there were in A. So the point is I have to multiply by this factor to kill this factor. Now I have a sum of squares of Gaussians. And squares of Gaussians are chi-squared. And there's NA of them minus 1. Except I have to normalize by dividing by sigma squared in the calculation. So this is a chi-squared distribution with NA minus 1 degrees of freedom. So exactly because we divided, where's my F? It's exactly because the definition of F divides out the degrees of freedom that I want to divide by this thing. Let me say that again. Let me say that again. I think I can do this. I want to keep this F distribution visible. Let's do a little origami. Okay. So what is, if I want to make an F distribution, I want to take U divided by N over V divided by M, which means I want to take NA minus 1 SA squared over sigma A squared divided by its degrees of freedom. And what is its degrees of freedom? Taylor? NA minus 1. If the definition of U, the whole point of this is missing. The point of this is to show you that. Well, I guess I rewrote it, so I don't have to show it to you anymore. I'll undo my beautiful origami of folding a piece of paper in half. The whole point is that we get to divide by the degrees of freedom. And when we do that division, these two things exactly cancel. And what's left is sample variance divided by true variance on top. And the same thing happens on bottom. NB minus 1 SB squared over sigma B squared divided by NB minus 1. So these exactly cancel. I get an SA squared over SB squared, and the sigma's in the opposite order. I get an SA squared over SB squared with sigma B squared over sigma A squared. And that is an F distribution, which, by the way, you should specify which one is which. So this is actually the F distribution with N comma M degrees of freedom. And it's ordered. It depends on the order, right? I can't just replace N and M and get the same distribution. By the way, what does this function look like? Let's say N and M are both bigger than 1 or something. What does this PDF actually look like? Let's graph it. Get a fresh piece of paper. Here's the PDF. This is T. It's only defined on the positive numbers. It's the ratio of two chi-squareds. Chi-squareds are positive. What's happening near 0? Let's say N and M are large. Let's not deal with the small cases. So N and M are each greater than 2. So that this is 3. So that this is a positive power of T. As T goes to 0, this part goes to 1. these things are constant. So I have a positive power of t near 0 that looks like 0. Okay, so it does that. And then it does something, I don't know what. And then what's the rate of decay? Well, for large values of t, this is growing. This is t to the n over 2 minus 1. That's growing. But for large values of t, this is decaying, like t to the n over 2. So this t to the n over 2 cancels that t over to the n over 2, but I have an extra t to the negative m over 2. So that is what is bringing this distribution back down. Okay, so that's the general shape. So it grows initially like t to the n over 2, I guess minus 1, in its initial range. And in its final range, it decays like, well, what's the power of t? It's t to the negative n over 2 minus m over 2 times t to the n over 2 minus 1. So in total, that is t raised to the point is that the positive growth is canceled by the negative growth, and we have certain negative growth. To the minus m over 2 minus 1. Can you see that? Let me make this bigger. T to the minus m over 2 minus 1. Again, it doesn't really matter. You're gonna, when you compute these tail values, you're going to do it numerically. But just so that you know mathematically what's going on, you have polynomial decay towards 0, you have polynomial decay out at infinity. Okay? What are we going to define these tails? We'll make a number. Let's call it f. It's an F distribution, alpha, with n and m degrees of freedom, is the number. So this is the number on the x-axis. This is in the t-axis. This is this number, so that the integral of this density out to infinity is equal to please say the word alpha. Yes, thank you. The letter alpha. Right? That's how you define this thing. That f sub alpha of nm is how far do I need to, how small of a t value do I need so that this integral is exactly alpha? Or how large of a t value do I need so that that integral, if I'm making alpha small, is that? Any questions? How are we going to use this distribution for testing for intervals? For confidence intervals. This ratio, we want to know the ratio of SA squared to SB squared. Sorry, we want to know the ratio of sigma squared A to sigma squared B. We can compute directly from the data the ratio of SA squared to SAB to SB squared, and we know what that is. That's an F distribution. So we're done. Let's compute. So, I'm running out of room. So, a 1 minus alpha percent, a 1 minus alpha percent confidence interval for sigma squared A over sigma squared B is given by, well, the probability that my F distribution, so my F distribution is SA squared over SB squared, sigma B squared over sigma A squared. The probability that it lies, again, I can't use the same number on both sides because the distribution is not symmetric, that this lies in some interval is equal to 1 minus alpha. That'll be our interval test. How much mass do you want to give to the high tail, which is actually the low tail because we're going to have to take the reciprocal? Let's say half. Let's say we put half the mass here, half the mass there. So if I put half the mass here, that means how much of the F distribution takes place up there? Well, that is F sub alpha over 2 with what degrees of freedom? Yeah, NA minus 1, NB minus 1. There's a reason we saved this one for last. It's the nastiest looking one, but it's absolutely conceptually no different from any of the other ones. how do we capture the initial bit of the distribution? We want to throw away the initial bit of this distribution. So we want to throw away this initial mass of alpha over 2. What's the point at which that happens? It's the point at which the tail is actually the bulk. So what is this point? This point, in terms of things we know, like things that we've defined. Yes?
F of 1 minus alpha.
Thank you, Jake, right?
Yeah.
Thank you, Jake. I know it's hot. It's hot and everybody wants to go to sleep. And we're almost there. So yes, exactly. It's f of 1 minus alpha over 2 with the same degrees of freedom. Na minus 1 and b minus 1. Okay? Any questions? Justin.
It's the same thing as writing alpha over 2, right? In this situation.
There's a symmetry. I wasn't going to get into this because people were lazy about tables. Again, you can just numerically ask the computer what this number is. But yes, the F distribution does have a symmetry in replacing A by B and this by 1 over itself. So that's simply because, look at how it's defined. It's defined, if I take 1 over this, I still get an F distribution. It's still the ratio of 2 chi-squareds. So 1 over an F is itself an F, just with the roles of the number of degrees of freedom switched. So you can use that to simplify this lower bound if you want to have fewer things to look up in a table. Once you use computers, don't bother. That's one extra fact I'm not going to quiz you. Jess and Deep had a question? Same question?
No, it was.
Okay. Other questions? Does this stuff make sense? We've done like a variation on a theme enough times, I hope, that now we can do it. We're not completely done because we actually want SA squared over, or sigma A squared over sigma B squared. But that's very easy to turn this into such. So if I want sigma A squared over, so this is equal to the probability that sigma A squared over sigma B squared lies between. So let's do this one. I multiply the sigma A, so that'll give me a lower bound. The upper bound here will give me a lower bound. If I multiply by sigma A squared, I divide by sigma B squared. I'm left with SA squared over SB squared divided by F alpha over 2, NA minus 1, and B minus 1. Right? Does everybody see that? So before, when we were doing point estimation, we would say, how can I guess what SA squared over SB, what sigma A squared over sigma B squared is? I would just guess that it's the value of SA squared over SB squared. But actually, I can get robust lower and upper bounds. One lower bound is F, alpha over 2, NA minus 1, and B minus 1. And the upper bound, again, it's going to be the same SA squared over SB squared, but now with the factor of this thing. F1 minus alpha over 2, NA minus 1, and B minus 1. So that is an interval depending only on things you compute numerically and things that come out of the observation. That is a 95% or whatever confidence interval for the ratio of two variances.